Welcome to lesson 2, graphing rational functions. So a rational function, as you would have talked about last year, is a function that contains technically two functions, one in the numerator and one in the denominator. So just like a rational number is anything that can be written as a fraction, rational function is any sort of equation that is written with both a numerator and denominator. So we've got a couple restrictions that are identified right away with rational functions, and that is that we're never allowed to divide by 0, and denominators essentially are doing division, so denominators cannot be 0. So that's what we're seeing here when we say this statement of this is a general notation for rational function. One function can be broken up into two smaller functions that are written as a fraction, but that denominator function cannot be equal to 0, and we're going to simply restrict p and q, those two smaller functions, in polynomial form. So that's what we're going to be working for this unit. So we've got some examples here. 1 over 2x plus 1. 1 is technically, quote-unquote, a polynomial. It's just a constant, but it still counts. Anything in terms of x with exponents is going to qualify, unless they are fractional or negative exponents. That's going to mess with some things, so don't worry so much about those. But if there's like a radical inside of a rational function, then we're going to have some different kind of problems, so we're not really going to work with those in this course. So if we consider the following functions in the table below, the graphs are already given, so that's kind of nice. You did some graphing of rational functions last year, if I'm not mistaken, so we're going to play around with that a little bit more, talking about non-permissible values and kind of what factoring does to our graph. And you definitely did some solving of rational equations last year. So if we start with our first one, y equals just 1 over x, our most basic rational function we can get. There is no way to factor this. It's impossible. So it stays as is. Key thing to note here is we've got some asymptotes going on at x equals 0, and here at y equals 0. So our non-permissible values are that x cannot be 0. And the y cannot be 0 is simply a result of this. And so we're simply going to look at what our x non-permissible values are for these functions. So it can't be 0 because we're not allowed 0 in the denominator. When we look at the next one, we see, and just to give you kind of a point of reference, if we just looked at the denominator polynomial, it would have looked like this. Okay, and so you'll see that we get that vertical asymptote where our original graph crossed the x-axis, where y was equal to 0. Where that output was equal to 0. Similarly, if we look at our parabola for this particular function, so y equals just x squared, if I consider that, it would look something like this. And so again, we don't really have to factor it per se. If you wanted to, you could write it as y equals 1 over x times x, but I don't know if that's 100% necessary. What we see is, again, when our original graph hits our x-axis and has an x-intercept, that our rational function then has an asymptote or some sort of non-permissible value. Okay, and so that asymptote is coming in the form of our actual graph extending upward forever but never actually reaching this y-axis where x equals 0. Now always remember that we name the vertical ones x because that's the value that defines them. Horizontally they get named y because that's the value that defines them. So if we were to list our non-permissible values here, we would say x cannot be 0 again. And again, that comes down to it being our x-intercept of our original function. It would be where our denominator equals 0. Third graph is a little weird because it looks the same as our previous one, but then we've got this weird part at the bottom, but don't worry, that will be explained. And we can do it one of two ways. Number one, we can do it by factoring. So we can put it all into, if we factor the denominator, 1 we can't factor, so that stays the same. But we can factor this out. Once we have it factored, I can identify, well, what if the denominator equals 0? Or if we say the denominator can't equal 0, then x cannot be -2 or -3. With this information, we can look for and will successfully find asymptotes at x equals -3 and x equals -2. So with seeing that, we're kind of affirmed this way. Additionally, if I went to just graph this parabola, know my y-intercept is somewhere up here. If I factored it, I would know that those are my x-intercepts. It's opening upward, and it would look something like this. And if that is the case, there should be a point there, then again we see that our asymptotes are where our graph crosses that axis, the x-axis. Okay. We do always have invariant points when our output is 1, if the numerator is 1. So all of these ones have been nice so far. Again, in this case, though, x cannot be -2 or -3 to complete our chart. Where it gets tricky is when we have something in the numerator as well. So instead of being strictly at 0, we end up with a situation where we've got a denominator with x, but also a numerator with x. So, oh no! We cannot factor this, so there's nothing to write here, per se. But what we're dealing with is we're dealing with a situation that has shifted kind of over 1. So in terms of our actual rational function, I can still identify my asymptote by defining my denominator as not being equal to 0. So x cannot be 1. So we see that happening. Okay. What's weird then is that instead of my horizontal asymptote being a 0, which is what my gut might have told me based on what we saw in the previous 3, my horizontal asymptote actually is at +3. And we're seeing this happen because specifically that 3 in the numerator. So when we have matching degrees, we might, and we have coefficients, this is resulting in a shift of horizontal asymptote. Okay, so again, we see that asymptote showing up here. Now, horizontal asymptotes are less of a concern in grade 12 and more of a concern in calculus, but just kind of as a heads up, not 0. force of habit 3. But the key thing is that that vertical asymptote is still easily defined by saying that my denominator can't be 1. This is not the case in our next example, where we have this equal numerator and denominator. So though we can't factor it, what I would really love to do is just rewrite this and say, well, anything divided by itself is just 1. So it's just all 1. And that's great. And that's really what we end up seeing. We look at our graph and we see this horizontal line at y equals 1. Amazing. The problem is that we get this little spot at x equals 1. And that is the result of the fact that even though we could cancel it out and divide it out and make it kind of disappear, we need to be true to that original function, that original rational function, and acknowledge the fact that we do still need to have a non-permissible value that makes this even possible. So I still have to identify that x cannot be, or x minus 1 cannot be equal to 0, and so x cannot be positive 1. But because it can be canceled out, it means that I no longer actually have a rational function anywhere else. I can kind of ignore it once I honor this piece, once I honor my non-permissible value. I can cancel out my denominator, I can cancel out a piece of my denominator, and I can draw my graph, and it's going to look way more like the function of my new equation than my original one. And that's what we see here. So that horizontal straight line matches this perfectly. But we need to honor that whole, which is coming from my non-permissible value. So we've got a few more examples to look at. So if we look here, we've got x squared minus 1 over x plus 1. Well, that looks like a linear graph with a hole in it. So automatically, holes tell me, red flag, I've got a non-permissible value that disappears. And I can define that by, again, checking my original function, looking at my denominator, saying 0 cannot be equal to x plus 1, and so x cannot be equal to negative 1. And that's exactly what we're finding here. But I can factor my numerator in this case, because it's a difference of squares. And this is what creates that hole, is the fact that I can take out the x plus 1s. Because x plus 1 divided by x plus 1 is just 1, leaving me with x minus 1. And that's what we're seeing when we draw the graph, is that this defines the shape of my graph. And it is a linear equation. And we just have a hole when x would have otherwise equaled negative 1. Because x equals negative 1 is a totally valid value. It's part of my domain in my new function. But I need to honor the fact that I canceled it out here. In this case, this looks really, really weird. So we get some asymptotic behavior because of our non-permissible value and the fact that nothing can cancel out. There's no way of factoring this out to make x minus 1 appear. So no factoring. And I need to honor my non-permissible value, saying x cannot equal negative 1, 0. So x cannot be positive 1. So again, we're still going to expect that sort of asymptotic behavior at x equals 1. The tricky part is that the farther we move away and the bigger the numbers we get, that square, that higher degree in the numerator than the denominator, it results in sort of a parabola-ish sort of shape that starts to mirror more the quadratic equation than the linear one. So if we have a higher degree in the numerator, that has a greater impact on shape. And again, that's what we're seeing with this kind of like weird parabola. It's parabola-esque. Our next one, well, this looks more like a reciprocal function again, so that's at least moderately comforting. What's happening here is, well, let's factor it out. These are both difference of squares, so x minus 1, x plus 1 in the numerator, x minus 2, x plus 2 in the denominator, which means that there's no cancellations, so there's going to be no wholes. So when I go to do my non-permissible values, for x, I'm going to set my denominator equal to 0, not equal to 0. And I don't need to include my numerator because my numerator is totally valid in being 0. I can have nothing and divide it into as many pieces as I want, and I'm still going to have nothing. And so x cannot be plus or minus 2. And we see that again in those asymptotes. So again, if we have a non-permissible value and canceling of that non-permissible value in my original equation, I'm going to get a whole. If I can't cancel out that denominator at all, then I'm going to have an asymptote. That's the big difference between those two pieces here. Otherwise, it's a matter of plugging in values, trying to figure out what exactly is going on. Because that denominator has a slightly different, larger value in terms of its constant, and my degree is exactly matching, that's going to kind of dictate where my 0 value ends up there. So it should be at 1/4. And then we see that happening here. So our graph kind of spreads out a little bit more. But again, you can generate that from a table of values. No problem. Being able to identify those asymptotes and wholes, though, that's going to be your key kind of piece of information that you're practicing from this. So our second last example, y equals, so if we factor this, oops, back to black, again, that difference of squares is happening in the numerator. And unlike the previous ones, this isn't a difference of squares, but it is a factorable quadratic. I get x plus 2 and x minus 1. And again, I notice, oh, I can cancel these out. That's great. That simplifies what I'm going to end up graphing in the end. But in the meantime, I also need to honor this fact. So when I do my non-permissible values, I still need to write the whole thing. 0 can't be x plus 2 times x minus 1. So x cannot be 1 or -2. But again, because it canceled out, I expect this to be a whole and this to be an asymptote. When we look at our graph, that is exactly what we see. We see that vertical asymptote at x equals -2, but just the whole there. The reason that I have that vertical shift in my horizontal asymptote is again because of that constant in the numerator. So things to watch out for. For our last example, if you want to pause right now and give it a shot on your own, you can definitely do that. I would encourage you to give it a go just in terms of practicing your factoring skills and predicting. So again, pause the video now and give this last one a shot on your own. If I factor it, and I look at it right away, I see that it's the numerator and the denominator are the same, so they're going to cancel out. I'm still going to factor it so that it becomes easier to identify those non-permissible values. So it's going to be x plus 1, x minus 1, because it's a difference of squares, The denominator, again, because they're exactly the same, is going to factor out the same way, which means that my non-permissible values are that denominator piece, x plus 1, x minus 1, can't be 0, so x cannot be plus or minus 1. But because everything cancels out, again, when things cancel, that means that it's a whole, not an asymptote, so I would put a whole here and a whole here at negative and positive 1. But otherwise, it looks like a horizontal line at 1, because when everything cancels out, what we're left with is y equals 1. Because again, anything divided by itself is 1. And this is where watching out, because canceling, multiplication, and division results in 1, not a 0. Only adding and subtracting cancel out to be 0. So that's where that language kind of becomes a little bit weird. So always watching out. If everything else goes away in terms of multiplication and division, you can expect it to be a 1 that's remaining. So in our notes, what can we say about rational functions? We determine the non-permissible values by setting x, or a denominator rather, equal or not equal to 0. And then if we're dealing with anything that can be factored, check for factoring, especially with degree of 2 or more, and solve for x. Okay, or isolate x. Okay, how can you tell whether a graph of a rational function has an asymptote or a whole? Well, as I mentioned previously, asymptotes are non-permissible values that can't be canceled out. Whereas wholes are non-permissible values that are not left in simplified form, or not apparent in simplified form. Finally, how can you tell whether a graph of a rational function has a horizontal asymptote? Basically, you're going to be looking for end behaviors and looking at the idea of if you're left with something in the denominator, then you are going to have some sort of horizontal asymptote. If you are left with nothing in the denominator, then you won't have a horizontal asymptote. Okay, so those are kind of our big ideas of this lesson. Summarizing rational functions. So you're going to have some practice for graphing rational functions. I didn't find any homework that really jived quite well with lesson 1. I'm still looking for some, but I'm going to hopefully be able to find some practice questions, especially for lesson 2, in terms of graphing rational functions, because those are some interesting principles that we have going on here. So like usual, ask questions and let me know if you need any help with anything.